Welcome back to the messy workbench. Today we want to figure out or measure the spurious emissions on a radio. So this time it's just a handheld radio, and we want to do that with a spectrum analyzer. So we have here the Siglent SSA3021X, and to measure anything, we're gonna use the input port to input the signal. So we're gonna go ahead and read right here the warnings. So what we have to watch out is that the maximum input is 30 dBm at 50 ohms. Obviously our ham radio is at 50 ohms and also 50 volt DC. So what the heck does that mean, 30 dBm? So we know this radio here is a handheld radio, probably somewhere around 5 watts output. So the question is, can we hook it up right there with a coax cable and make our measurements? So we know 5 watts, 30 dBm. dB is a measure, is a differential of a differential measurement of power. dBm, the M refers to the specific power level it is at. Now I don't have it right off with me on it, what the value is, but you can look it up on your own. So let's go ahead and online there's a nice little calculator. That calculator helps us figuring out. So right here we have our 30 dBm at 50 ohms, and that equals to 1 watt. So what that means is we can input 1 watt into it. Obviously this radio transmits more than 1 watt, and even the 1 watt is the maximum, so we don't want to input 1 watt to it. So instead what we need to do is we need to attenuate the signal. For that we use an attenuator, something like this black piece here. That's an attenuator for 30 dB. It attenuates 30 dB. Its rating is for DC to 3 gigahertz, so we're fine with that. And we have a maximum of 25 watts. What that means is there's somewhere the power has to go, right? That we attenuate, and that turns into heat. So this attenuator can dissipate the heat for 25 watts. So we know that this radio is not 25 watts, so we should be fine with the watt rating there. But what exactly does 30 dB gain us? So let's go back to the attenuator and state the input energy into our spectrum analyzer is 1 watt. So we can increase the input by 30 dB and we get out 1 kilowatt. So that's quite amazing. We can input 1 kilowatt and we just then reach the maximum. So obviously we don't want to operate at the maximum. But again, remember that this here is only rated for 25 watts. So with 1 kilowatt it would just totally overheat, and that wouldn't work. So let's go ahead and type in some other numbers. So here we say we transmit with 100 watts into the spectrum analyzer using 30 dB attenuator again in between it. How much would go into the spectrum analyzer? And that would be 100 milliwatts. So theoretically that attenuation would work. Again, we have 25 watts there. Obviously the heat doesn't dissipate on that. So I definitely would not go 100 watts with this specific attenuator. Personally, probably around 10 watts is where I would stop feeling comfortable with that. So let's do a couple of other things here before we go in. So maybe we don't even know how much power this radio transmits. So let's go ahead and see if we can figure out how much power that transmits. See if this attenuator works, and then measure the spurious emissions. So before we go measure the power of the radio, I want to just double check, is the 30 dB that's written on this attenuator correct? For that we use our spectrum analyzer. So there is another hint on the spectrum analyzer, how to use it. We just go ahead and do the full spectrum to work with. So we don't have to change the frequency. If you want to reduce the spectrum that you're working on, you could type in 30 megahertz as the, no, that's the center frequency. Start, we could say 30 megahertz, and the end frequency is 400 megahertz. And so we would go from 30 to 400 megahertz. Again, go back to the full spectrum. And let's go ahead and take some coax cable. First, let's just do a quick test here on our setup, probably with the coax cable, to just calibrate our testing. So we take this setup here. We need, where's the adapter that I need? It's not the adapter I need, this adapter I need without this attachment. So I'm gonna attach that one sec. Okay, so I have two coax cables and have here a whole bunch of barrel connectors here. That's just so I can easily insert the attenuator right on here and on there. And with that we measure all kind of effects that all of these adapters have. So what we want to do is we want to we are using the spectrum analyzer source, so that's a signal that it sends out from our starting frequency to the stop frequency, and then on our input side we are measuring what we get back, so we can very controlled measure our device under test. So we go ahead and start the trigger generator. We press the TG button, and on here we get the menu where it says TG off. So we go ahead and turn it on, and then we press the normalize button. And the normalize now makes it nice marked to 0. So this is what calibrates our test setup here. Now we can go ahead and put in the attenuator. Okay, I went ahead and inserted the attenuator into our test setup here. I did not change any of the controls here from our calibration, so it's still calibrated as before. And we see right here the signal drops down to about -30 dB, and it's fairly straight across. So if we wanted to see specifically our frequency, let's go ahead and just zoom in to the 2 meter frequency range. And to do that, I'm gonna calibrate again. So I'm gonna take out the attenuator out of here, and then set up the system for the frequency range. Okay, the attenuator is removed again. So we go in here, touch the frequency, and say our start frequency is at 144 megahertz. Now stop frequency is at 148 megahertz. So it's still actually pretty good to calibrate it, but let's go ahead and do that again. So we go back to the trigger generator by pressing the TG button, turn off and on the normalization, and we have a nice even line up there. So let me put in the attenuator again. And the attenuator is back in. Looking up at the spectrum analyzer, we have a nice clean 30 dB attenuation. So we are good with that. So let's go ahead and measure the power output of our radio and then see what that would do to the attenuator. Let me prepare here the setup. So what we basically want to do is we use our dummy load, which is the 50 ohm dummy load in which we transmit. Then we use our power meter. I don't have anything good fancy, so we just use this here. It's gonna be good enough to get us in the ballpark what we're working with. So let me set that up. Okay, so I set up everything without the attenuator, and we have the radio here. So I'm gonna go ahead and try. Oh, on the scale we set it to 30 watts maximum. So we are reading on the top scale the bottom number. Right here is 30, the maximum, and we'll see how much power we get. So if you go ahead and transmit, we see here a nice 5 watt being transmitted. Now we change our setup. We have the attenuator in there, and when we transmit, we don't even see any kind of a deflection there. It's such a weak signal. If you really closely look at it and I dial this down even more, see a small little jump there, just because of the attenuation is so high. So we are definitely safe to transmit that into our spectrum analyzer. So we are confident that we can go ahead. So let's go and set up this here for the actual test with the spectrum analyzer. And for that, all this is going to be the same. I'm just going to hook up the coax cable to the spectrum analyzer. Let's go ahead and do that. Okay, so now we set up everything. We have the radio, our attenuator going right into the spectrum analyzer, and we reset the spectrum analyzer. We don't want to have the limited range on the frequency, and we don't need a trigger generator, so we could change that all manually, or we just press reset. That takes me back to the factory default that I have here. So we are scanning again from 0 hertz, well actually 9.9 kilohertz to 2.1 gigahertz. The next thing we want to do is let's just go ahead and transmit. So if we transmit here, wrong button. If we transmit here, you see the peaks, and if I let go, they disappear again. So we have to transmit all the time while we look at it. To avoid that, we just go ahead and go to trace and click on max hold. That holds the maximum power on each line. So I can go ahead and transmit, and we see right here that stays now that I don't transmit any longer. Now we want to read the values on those peaks. To do that, the easiest way is we go into the peak menu, and here we can select the peak to the left and peak to the right, so you can jump that marker there over, and you see right up here the frequency as well as the dBm level. Or if we just want it simpler, we can click on the peak table. That's what I always do. And right here it tells us the frequency and the amplitude on it, along with the marks of those peaks. So we see that peak 1 is at 6.55 dBm and peak 2 is at a different dBm. So the 6.55 dBm, that actually tells us something. With the default setting, that's exactly how much power it reads off this connector here. So 6.55 dBm, we can do the math and calculate that how much wattage that is. but we spent the money, so we don't need to do any math here. We just go to amplitude and then go to units and change it from dBm over to watts. And voila, we see that that's 4.52 millivolts. And that's how much we transmit into the spectrum analyzer. That's good to know, but we also would like to know how much power does this radio transmit. To do that, we can go again back to the amplitude settings right here. And on the bottom right here is the reference offset, 0 dB right now. And we have a 30 dB attenuator in there. So we just change this value, press the button here, to 30 dB, select dB, and voila, we specify 30 dB as our reference, and the values, well, the peaks disappeared. So we have to transmit again, since we did change, the memory didn't keep. So we go back to trace, we still have max hold on, and I go ahead and transmit. And now we see right down here 4.52 watts. That's how much our radio transmits. That's exactly kind of what we are expecting here. So we are right on the money. We want to see more about our spurious emissions. We definitely see that we have some, these are the spurious emissions. And if you look at the values of the frequency, those are the harmonics. So now we need to figure out, are those significant enough that we need to worry about them? And there are a couple of ways to read these spurious emissions. One is via decibel. So we go back to amplitude, press amplitude, and change the unit back to dBm. And now we see that our fundamental frequency, that's the frequency we transmit, is at 36.33 dBm, and our highest, that would be this spurious emission, is at 10.69 dBm. So what that means is there is a difference of, from this peak to that peak, of, we just add them together, so it's 46.9, actually a little bit more than that. So you just add the 36.33 with 10.69 together, and that's the dBms between 0.2 and 1. So in the FCC rulebook, we have a specific decimal it needs to be below under certain circumstances. Under other circumstances, we have a specific wattage that the spurious transmission cannot go over. So again, for that, we go over here for the units and choose the wattage. So right here we can see that the spurious emission of 2 is 85.22 microwatts. So if you do testing, there's another thing that comes in handy. That is the putting in the baseline under which the spurious emission needs to be. For example, here in the States, for 2 meters, it needs to be under 25 microwatts. So we go over here, press display, and we go to the display line and turn that on. Type in 25 and UW for microwatts. So now we have this nice little orange line here that we know the emissions needs to be below it. And at this point we see already on a glance that on the second harmonic it's above it. The third harmonic and fourth harmonic are pretty close, so I would recommend just switching this table over to watts and then read off the values here. So we see here 82 microwatts, that's too high, and 14 and 12, those are okay. So that's how you measure the spurious emissions. Have a good one. Until the next video.